Time remaining. During downloads, your download starts. A tiny window pops up and confidently declares 2 minutes remaining. You relax. 30 seconds later, it changes its mind. Now it says 4 hours. You panic. Then, before you can process the betrayal, the download finishes. The file is on your desktop. The estimate was performance art. Here is what actually happened. Your computer does not know the future. It cannot predict network congestion, server throttling, or whether your roommate is about to stream a movie in the next room. So it does the only thing it can do. It looks at the last few seconds of download speed, measures how much data just arrived, calculates an average, and assumes that average will continue forever. This is like predicting your road trip duration based solely on the last 10 seconds of driving. If you were stuck at a red light, your computer would tell you the trip will take 6 days. When the download starts, the first kilobytes arrive quickly. The calculation is simple. Small file, fast speed, 2 minutes total. Perfect. Then the network hits a slow patch. Maybe the server is busy. Maybe your router is prioritizing another device. The speed tanks. The formula recalculates. Same file size, much slower speed, 4 hours remaining. Your computer is now convinced you will be waiting until dinner. But networks are not consistent. A moment later, the congestion clears. Data floods in. The progress bar leaps forward. The estimate does not even have time to update before the download completes. Fake progress bars? You click install. A progress bar appears. It glides smoothly from left to right, filling with a pleasant blue gradient. You watch it move. It feels productive. You assume work is happening. Sometimes it is. Often it is not. Progress bars exist to stop you from killing the process. If an installation sits frozen with no visual feedback, you assume it crashed. You reach for the task manager. But if a bar is moving, even slightly, you wait. You trust the motion. That is the entire point. Real progress is jagged and unpredictable. A software installer might spend 3 seconds copying files, then 40 seconds verifying signatures, then 2 seconds writing to the registry. If the progress bar reflected this honestly, it would stutter, freeze, and leap forward randomly. Users would panic. So instead, the bar moves smoothly. It advances at a steady rate even when the underlying work is stalled. Some progress bars are real. They count files copied, bytes written, tasks completed. But many are animated timers. The system guesses how long the process will take, sets a duration, and moves the bar accordingly. This app is not responding. A window freezes. You click inside it. Nothing happens. You click again. Still nothing. A few seconds later, the title bar goes pale. The system adds a label, not responding. You sigh. You assume the application is dead. You consider force quitting. But sometimes, if you wait, the window flickers back to life. Everything you clicked suddenly executes at once. The app was never broken. It was just busy. Here is the technical reality. Your operating system expects applications to respond to interface events quickly. When you click a button or move a window, the system sends a message to that application. The application is supposed to acknowledge the message almost immediately, even if it cannot complete the action yet. But if the application is doing something expensive, like processing a giant file or waiting for a slow network response, it may not check for new messages. It is too busy working. The system sends a message. No reply arrives. After a few seconds, the system gives up and marks the application as unresponsive. The label is not wrong. The app genuinely is not responding to the interface. But that does not mean the app has crashed. It just means the app is ignoring you while it finishes what it was doing. Battery percentage. Your laptop battery reads 53%. That number sits in the corner of your screen, crisp and specific. It feels scientific. Then you unplug the charger, open a browser, and the number drops to 41% in 30 seconds. Or you reboot, and suddenly you have 60% again. The battery did not gain charge. The estimate just changed its mind. Batteries do not report their charge directly. They cannot. A battery is a chemical system, not a fuel tank with a floating gauge. Instead, the system measures voltage. It watches how the voltage changes under load, compares that to a reference model of how batteries behave, and calculates a percentage. This model is a guess. It assumes the battery is healthy, that the temperature is stable, that the load is predictable. When any of those assumptions break, the estimate breaks with them. Voltage does not decline in a straight line. When you launch a demanding application, the battery voltage dips. The system sees the dip and recalculates. It now believes you have less charge than before. The percentage drops. You did not lose power. The model just updated its opinion. Rebooting resets the estimate. The system takes a fresh voltage reading without active load. The number is higher. The battery looks healthier. The percentage jumps upward. Nothing physical changed. The measurement context changed. Storage space reporting. You delete a massive folder. Gigabytes of files disappear from view. You open the storage settings to admire your new free space. The number has not changed. You deleted the files. The system agrees they are gone, but the disk is still full. You feel like you are being mocked. In a sense, you are. Deleting a file does not erase it. Deletion removes the file from the directory listing and marks the space as available for reuse. But the actual data remains on the disk until something overwrites it. That is not the main problem, though. The main problem is that your operating system has created silent copies of everything you think you deleted, and it has not bothered to tell you where they are. Your system maintains snapshots. These are point-in-time backups of your entire drive, captured automatically in case you need to roll back a disaster. When you delete a file, it vanishes from your current view, but it still exists inside every snapshot taken before the deletion. Those snapshots consume space. They are not included in the normal storage breakdown. The space is occupied. The interface pretends it is not. Then there are caches, temporary files, thumbnail databases, browser data, application logs. These accumulate constantly. The system is supposed to clean them automatically, but the cleanup is sporadic. A cache might grow to several gigabytes before the system decides to purge it. The storage calculator does not always account for these in real time. You are up to date messages. The system announces that everything is current. A notification slides into view. Your system is up to date. You feel reassured. 10 minutes later, another notification appears. Updates available. Restart to install. You did not do anything. Nothing changed. The system lied to your face, then immediately confessed. Operating systems check for updates by contacting a remote server, but this check does not happen constantly. It happens on a schedule, maybe once a day, maybe once a week. Between checks, the system has no idea if new updates exist. When you open the settings and see up to date, that message reflects the last check, not the current reality. If that check happened 6 hours ago, the message is 6 hours old, but it displays as if it is current. The system is not refreshing the information every time you look. It is showing you cached state. Then, moments later, the scheduled check runs in the background. New updates are available. The status flips. Suddenly, you are out of date. Sometimes, the system lies because the check itself failed. Network errors or server timeouts can prevent the update query from completing. When the check fails, the system does not say, "I could not verify." It says, "You are up to date." Wi-Fi signal strength, 4 bars. Full signal. Your Wi-Fi icon glows with confidence. You open a browser. Nothing loads. You refresh. Still nothing. The icon still shows full bars. You are connected to nothing, but your computer insists the connection is perfect. This is not a bug. This is working as designed. Wi-Fi signal strength measures one thing only: the quality of the radio connection between your device and the router. It tells you how clearly your computer can hear the router and how clearly the router can hear your computer back. That is all. It does not measure whether the router is connected to the internet. It does not check if the internet service provider is experiencing an outage. It does not verify that the router has assigned your device a valid address or that DNS is functioning. It just measures radio waves. You can have a perfect radio link to a router that is completely disconnected from the outside world. Your computer will report full bars, while you have zero access to anything beyond your living room. The bars also do not account for congestion. A router can have excellent signal strength and still be overwhelmed. If 20 devices are all streaming video simultaneously, the router may not have enough bandwidth to handle your request, even though the wireless link itself is flawless. The signal is strong. The data is stuck in a queue. Your computer sees the radio connection and assumes everything is fine. It is not fine. File, successfully deleted messages. You select a file. You press delete. A confirmation appears. File successfully deleted. The file vanishes from the folder. You check the recycle bin, empty it, and move on with your life. The file is gone, except it is not. Copies exist in at least 3 other places, none of which the system mentioned. Deletion removes the file from the active file system. The directory entry is erased. The storage space is marked as available, but the operating system does not go hunting through every corner of the disk to eliminate traces. If the file was recently opened, a thumbnail might exist in the image cache. If the file was indexed for search, a copy of its metadata and possibly its content sits in the search database. If you have automatic backups enabled, a complete copy exists in the backup archive. If you use Cloud Sync, another copy is on a remote server. The file you deleted is gone from the one place you were looking. It persists everywhere else. System snapshots complicate this further. Many operating systems take periodic snapshots of the entire disk state. When you delete a file, it disappears from the current state, but every snapshot taken before the deletion still contains the file. Those snapshots are hidden from normal view. They do not appear in your file browser. They occupy disk space. The file is inside them, intact and accessible if you know where to look. The system will eventually age out old snapshots, but that might take weeks or months. Until then, the deleted file is still on your computer. Privacy indicators. A green dot appears next to your camera. The system is informing you that an application is accessing the camera. You feel reassured. The indicator is there to protect you. If the dot is off, the camera is off. That is the implied promise. The reality is narrower and more technical than you were led to believe. The indicator reflects application level access. not hardware-level activity. When a program requests camera access through the operating system's official interface, the system knows about it and displays the indicator. But not all camera access goes through that interface. Drivers, kernel extensions, and low-level system processes can interact with hardware directly. These do not trigger the indicator because they bypass the layer that controls it. The camera can be active, the light stays off. Privacy indicators also do not distinguish between active use and passive permission. An app can request camera access, receive permission, and hold that permission open without actually capturing video. The indicator turns on because the access is granted, not because the camera is recording. You see the dot, you assume you are being filmed. The app might just be holding the resource idle. Shutdown versus sleep behavior. You click shutdown, the screen goes black, the fans stop, the lights turn off. The computer appears to be completely powered down. You assume it is off. It is not. Parts of the system remain active, waiting, listening, ready to turn back on without you touching anything. Modern computers do not have a simple off state. They have a cascading series of low power modes. When you select shutdown, the operating system closes all applications and sends a power down signal to the hardware. But the motherboard does not cut power entirely. It leaves certain circuits energized. The network interface remains partially active so it can listen for wake on LAN packets. The USB controllers stay powered so a keyboard press can trigger a restart. These components draw milliwatts, but they are absolutely still consuming electricity. Sleep mode is even more deceptive. The system writes the current state of memory to disk, then enters a suspended state. The screen turns off. The fans stop. The device looks dead, but the memory remains powered. Background processes can wake the system to perform updates, check for messages, or sync files. You put the computer to sleep at night, you wake up and find it warm, the fans running. It woke itself up at 3 in the morning to install an update, then went back to sleep. Error messages that explain nothing. Something went wrong. That is the message. 4 words, no details. No error code. No hint about what failed or why. Just a vague acknowledgement that the universe did not cooperate. You stare at the message. You click OK. You try again. The same message appears. You learn nothing. Error messages are simplified on purpose. The actual error is often a technical cascade involving memory addresses, failed system calls, or network timeouts. Showing the real error would overwhelm most users. So the system translates technical failure into human-friendly language. The translation loses all specificity. Your data is safe claims and the core reality. The system promises your data is protected. Encryption is enabled. Backups are running automatically. Everything is secure. You feel confident. Then a drive fails, or a ransomware attack hits, or you accidentally delete the wrong folder, and you discover that safe meant something far more conditional than you thought. Encryption protects data from unauthorized access. If someone steals your laptop, they cannot read the files without the decryption key. But encryption does not protect against accidental deletion, hardware failure, or corrupt file systems. If the encrypted drive dies, the data is gone. The system told you the data was safe. It meant safe from one specific threat. You assumed it meant safe from all threats. Backups are supposed to solve this. Your system creates automatic backups to an external drive or cloud service. You assume this means copies of everything, stored reliably, ready to restore at any moment. But backup systems have limits. Some only back up user files, not system settings. Others exclude large files to save space. Some run on schedules that leave gaps of hours or days between snapshots. One misconfiguration breaks everything. You enable encryption but forget the recovery key. You set up backups but point them to a drive that fails. Computers do not lie. They approximate reality through models, estimates, and human-friendly abstractions. Every status message is a translation of something technical into something you can understand. The translation is lossy. Details disappear. What remains is simplified truth presented as whole truth. Your computer is not lying to you. It is just speaking a language that cannot express the full truth without becoming incomprehensible. And speaking of things being kept from you, check out the next video on the 7 levels of how tech companies spy on you.